Hello guys. So today we are going to quickly to start, not to start but to finish, to complete our how can I say, our chapter. Okay, the theoretical part of our chapter about higher order, higher order, um, higher order homogeneous constant coefficient differential equation. Okay, so now I'm just here to summarize a bit. Okay, to summarize about what we have done during our last three videos. Okay, we found out that whenever we have a higher order homogeneous and constant coefficient differential equation, okay, uh, the solution can be expressed in mainly four ways, and we have demonstrated only three ways. And these ways are like when the roots are, how can I say, when we have real roots, okay, real different roots, so the solution of the equation will be expressed in this way, okay? And when we have real repeated roots, so the solution will be in this way. And then we have finally when we have imaginary different paired roots. So as we know that imaginary number are always arranged in pairs, yeah. So then we will have in this way. Okay, this will be the solution for any solution. Suppose we have any imaginary different pair roots, okay, or root pairs. So we have it this way. Now, from this basement, I will just deduce, because I will not just calculate anymore. I will not calculate. If I calculate, it will be a kind of boring. But if you feel like you want to do more calculation on demonstration of it, so you can continue, and I will give you the steps just to guide you to find the general formula when we have imaginary, okay, the fourth case that is here, when we have imaginary repeated pair roots, like, yeah. And I will deduce this formula only by watching what happened there, what happened here, okay? So when we have imaginary, imaginary, um, imaginary and equal or repeated, imaginary repeated pair roots. Okay, yeah, that's the point. When we have imaginary repeated pair of roots, how to write the entire solution? Okay, I will just compare, okay, by comparison. Because see, whatever we did in here, we did for this one. And the same concept that we did to find real different roots, we used to find imaginary different roots, okay? The same concept we will use to find imaginary and repeated pair roots. It is the same concept used when we found the real repeated roots, okay? So yeah, basically what you're going to have, it is like this expression. Look at this one, okay, just look at this expression plus this expression plus this expression, it's almost the same for different, like real different roots. Just compare these real different roots with imaginary different pair roots, okay? Compare this one and this one. Look here, we have alpha. Alpha is the real part of the imaginary solution that we have, okay? Of the one of the imaginary solution that we have, alpha. And see, alpha is the real part. Beta is the imaginary part. Now see, if you compare this Euler to this one, this part is the same as this one. Just comparing, okay? Euler, Euler. Okay, just comparing Euler, Euler. Second one, it is for the second one. The how can I say, the first root m1 is for alpha 1. This is one solution. The second one is for alpha 2. This is the second solution. Okay? You have just to compare. And now see, Euler 1, Euler raised to alpha 1, Euler raised to m1, just like this. It's fine. Now check, when we have real repeated roots, what happened? We have only one, okay, one real, one root, only one root that is repeated, okay? And we have this, how can I say this word? We have this exponent, not exponent, sorry. We have this, the arbitrary constant repeated in a factor of C1, X, and so on and on. And this expression is given by this general term like we have here, okay? Like x raised to n minus 1 Cn. For x, let's suppose for C1, how to obtain this C1? It's very simple. Just put here n equal to 1. You get 1 minus 1, 0. That's why here you do not have x, okay? Because x raised to 0, it will be 1. And here C1 will be the only one. And if you want to get the second term, just put n equal to 2 and you get this one, okay? Now it's fine. See, this is when we have repeated, okay, roots, okay, real repeated roots. Then I will compare these real repeated roots with the imaginary and repeated roots. What will happen here? That's the point. See, when I get these repeated roots, what does it mean? For imaginary, if I have only one repeated root, I will have this one. Alpha will be the only alpha for all of them. Okay? Alpha will be the only alpha for all of them. So what we are going to have here, CF will be equal to Euler raised to only one alpha times x. And here I will have repeated, okay, infinite repeated of this term, okay? I will repeat this one will be repeated, this one can be repeated, this one can be repeated, and so on and on and on. Okay, and so what should we do? Suppose just this alpha is the same. Just suppose this alpha is the same. Alpha is the same, alpha is the same, and alpha is the same. Okay, and this beta here is the same also. This B2, like a beta 2 is the same. Beta n to n term is the same. Okay, suppose all beta is the same and alpha is the same. How to write this one? I will just write Euler raised to 1 alpha, only 1 alpha, like this one, and only 1 beta. So what will be changing here? What will change if you see? It will be here. It will take C1 plus C1, I mean for x, okay? I mean for x, like, it will take C1, then I can just do C1 plus C2, okay, plus C3, okay, and then plus Cn, and so on and on and on. So the same concept that we applied here for repeated, okay, the way the arbitrary constant will be changing here in repeated roots that are real, it is the same way that this arbitrary constant will change, the very same way, okay? And this change will be analyzed or will be seen in this portion for cos, okay, for cosinus and for sinus. The only thing that will change here is that will be what? The number of roots that we are going to have, okay? Suppose it is 2 pair roots that are equal. Suppose I have 2 pair. This one and this one are equal. So I will have 4 solutions. And then what does it mean? For having 4 solutions, I will have C1 like this, C1 times x C2, C1 times x C2. Then cos of beta x and cos of beta x will be the same, okay, because they are repeated. This be 1, beta 1, beta 2 will be the same, and alpha 1, alpha 2 will be the same. So I'll get only this one and this one. So what we'll have here, I'll get this one, I'll get C1 plus x C2, okay, times cos beta x, because alpha and beta are the same, okay? It is only for 2 roots, okay? Now imagine if it is for infinite roots. So it will be plus, okay, plus x raised to n minus 1 Cn times cos beta x, okay? Cos beta x, then plus the second term for sinus, it will be the same, okay? It will be the same. Here we ended like C1 plus xc2 plus infinite sum, then plus x raised to n minus 1 times cn. And the same will happen here. Okay, plus I will add here plus I c1 plus x c2 plus infinitely sum, okay, plus sinus of beta x, okay, sorry now, okay, infinitely sum x raised to n minus 1 times cn, okay, close bracket, cn beta x. Okay, yes, that's the way we write the solution for infinite, okay, for infinite repeated, okay, infinite repeated pair of roots. Okay, now that we are done, just grab it online, take it online, okay. If it is possible, just make a picture of this, because this is very important. So this one we use when we have real different roots, okay, we can just use that. M1 is the first root, M2 the second, and so on and on. And here we will use when we have real repeated roots, okay. M is the root that is repeated, the same root, then this solution will be like this. Then imaginary pair, imaginary different pair. So when it is imaginary, okay, when the solution is imaginary, and we know imaginary number when it is solution, so they are always in pair, okay, just like this. Then we find what is CF, and CF for this one will be this. It is already demonstrated in the video, in the previous video. Then for this one, just by analyzing what we did before, this can be checked easily, okay? Yeah. Okay, now we are going to see some exercise so that you can have more understanding about these equations. Okay, nice. Let us see what we have here to bring up. Okay. See guys, but before I start solving the exercise, I'd like just to introduce a new term, we know that when we started solving those equations, like y double dash plus 6, suppose 6y dash plus 9 equal to 0. When we start solving these equations, okay, we used, how can I say, we used the normal way to find the solution and so on and on, okay? But sometimes to make it easier, okay, to make it easier to people, we can just use something called what I can say, something called auxiliary equation, an equation to help you to deal with this equation, okay, in a different perspective. And the auxiliary equation is something like, you see, actually if we just go back to the video, we will see the auxiliary equation, but in a different form, okay, just as constant and things like that. But now let us just introduce what is our auxiliary equation, okay? Like, what is the auxiliary? What will be the auxiliary equation? What is that auxiliary equation? It is auxiliary equation, it is the equation that you write, okay? It's an equation of, how can I say? It's an equation, suppose we have this expression like here. Let me write the general term, and suppose we have here y raised to n plus a(n minus 1, y raised to n minus 1, then plus finite sum a1 and here y raised to 1, okay, y raised to 1, then plus a0 and here only y, okay, it's equal to, no, it's okay, a0 here, rest to 0, 1. Now see, what we are going to have, suppose we have this expression, okay, a1, sorry, a1, okay, yes. What you are going to, how to solve this? Suppose we have this expression. We know that this is a higher order constant coefficient, and it is homogeneous differential equation. So what is auxiliary equation? So auxiliary equation, it is the equation, okay, where we have to consider this part over here. We have to consider d, okay, like the operator d of the x, okay, just the operator. Just consider the operator as it is equal to d. So what we mean by that, okay? We know that y raised to n here is the order of the differentiation here, okay? So it means that here, if I want to write this expression, this should be something like a, it's the same as a and d dx, okay? d dx y raised to n plus a n minus 1 d dx y raised to n minus 1, and so on and on, okay, so on and on. And here what we are going to have, here we have y, right? So okay, just this way. So here we have this expression and this expression, okay, and here also a, okay, and here we know that this is like a1 and y. We can just write it does that this one as it is, okay, like this, okay, a1 and y, and this is equal to 0. Now see what is happening here. So if I write okay, this, if I write this equation, just, okay, taking your y is common, okay, just take your y, because here, even though this n is the order, it's nice, but what is your argument here? Your function is y. If you take common this y, and this y, what will happen here? You will end with a n time d dx, okay, d dx, okay, with this n, sorry, this n is not, this y is not here, it is in here, and this n minus 1 is in here, sorry, okay, yeah, this is only y here, yes. Now if you check this expression right here, y is our independent, is our dependent variable, y here is our dependent variable, here it is independent variable. Now check, if I just take common this y and this y here and this y here, what should I have? I should have an equation like this, okay, the operator of this one, this operator, okay, this operator like this one, okay, plus a n minus 1 and d n minus 1 raised to n minus 1, and here without any operator, and x plus goes to infinite plus a1, all of this multiplied by y equal to 0. Yeah, this should be your equation, okay. So when you do this, okay, what you have here is what we call, okay, let me just adjust this one, okay, what we have here, okay, what we have here is what we call auxiliary equation, okay, this is auxiliary equation. So if I substitute where I have d, or where I have d upon dx, where I have this cofactor, okay, here where I have this cofactor, substitute just by d, what will I have? I will have something like this, a raised to n d raised to n plus a raised to n minus 1 d raised to n minus 1 plus a, okay, plus infinite sum here, up upon this one 8 1, okay, equal to y, and this is equal to 0. Okay, so it means what? That's the question. What does it mean? It means that surely what we are going to have here, it's an equation, okay, and this equation will be based upon d. So we will find d, and after finding d, okay, after finding d, what we are going to see, we are going just to check whether this d is, the solution of d is a real repeated root or not. Then we will apply that formula that we have studied, and we will see, suppose d has solution, sorry, suppose d has a like infinite different real roots, so we will use those formula. Suppose d, it is like infinite imaginary repeated solution, so we will use those formula and so on and on and on. Okay, in a nutshell, this is your auxiliary equation. Suppose for this equation, how to write the auxiliary equation for this one? So this equation, the auxiliary equation for this one, it will be y dash 6y dash plus y equal to 0. Now just consider that you are taking out your y, your dependent variable y. If you take out your dependent variable y, okay, take out your dependent variable y, make d dx, okay, is equal to d. So what you're going to have, d, the order is 2, plus here 6, the order here is 1, then plus 1, okay, time y equal to 0. Okay, what is your auxiliary equation? Your auxiliary equation will be this one only. Forget about this y. Okay? Yeah. And this is not a multiplication. Okay? Just understand. This is like, this is a property of derivative. Okay? So whenever I just have this derivative of here, this one and this one, so if I multiply, if I just pick this up, okay, this is the function and this is the operator. So I just separated the function from its operator. Okay, so that it will be true even if I want to put it back to even if I want to put back the function with its operator, so that I can just derive this function normally. It's like when I have like suppose I have like d upon dy, and here it is x. Okay, this can be written like this: d dy, okay, d dy, okay, and here it is like d dy of x. Okay, we know that this will be what? This is operator and this is the function. So we just have to put this one, that is independent variable upon here, and it will be back. This is what we did here. Okay. Yeah. Then we find just the root of this operator. After finding the root of this operator, we analyze the root of this operator, whether this is real, whether this is imaginary, or whatever. Okay? And this is the way we are going to use to solve these problems, okay? By applying auxiliary equation. Because I use those ways just to demonstrate, to show where those exercises or where those formula were coming from, okay? So here, so the auxiliary equation will be d squared plus 6d plus 1, then is equal to 0. Then find, sorry, it's not 1. Sorry, it's 9. 9y. So it is 9. Then it is 9. Now what comes here after? It is nothing more than basic. Okay. What comes after? What comes after? It is basic like simplification and basic factorization and basic concept of equations. Okay. Now see, I will just solve this one. So d squared plus 6d plus 9. This will be d plus 3 squared. Okay. Why? Okay. Because we know that this is the addition of the roots, and this is the product of the roots. So 6 and 9. What is the number that you can multiply? Okay, that you can multiply two numbers. Just imagine in two numbers that you can multiply, gives you 9, and you can add them, you can sum them, give you 6. This is 3. Okay, because when I have like b squared plus 6d plus 9 equal to 0, just imagine two numbers that you can add will give you 6, and you can multiply will give you 9. So 3 plus 3, 6. 3 times 3, 9, and that's done. So D, okay, let me use the different one, a different color. Okay, so D square plus 6D plus 9 equal to 0 will be D plus 3 and D plus 3 equal to 0. Now see how to find this one. This will be D is equal to 3 negative, okay, and the other one is also 3. You see, here you have two roots that are equal each other, and they are real. When we have two roots that are equal and are real, what should be the solution? Our CF should be Euler raised to mx, and here C1 plus x C2. Okay, yeah, just this is very important to you to understand, okay, why we were writing those formulas. So here we have two roots equal and are real. This is the solution. Now CF here, just substitute what is m. M is your root, that is common, minus 3x, and here C1. What is C1? C1, we don't know. This is C1, okay, plus x C2. And that's the solution. Okay, that's the way we found the solution. Okay, now let me solve just for another one, another exercise. Nice. Let us do. Suppose we have y. There's 1 plus 6 my double dash plus 12, yes, plus 12 y dash and plus 8 equal to 8y equal to 0. Suppose we have this equation over here. Okay, so how to solve this kind of equation? That's the question. That's the point. See, this is y cubed and so on and on and on. First, write the auxiliary equation. What should be the auxiliary equation? Just imagine this will be d raised to the order 3 plus 6d squared plus 12d and plus 8, okay, equal to 0. So the auxiliary equation is only this part, okay? You can just forget this one. Yeah, this is equal to 0. Now find what will be the solution. Now see, just by comparing this one, okay, this is a cubic equation. So for cubic equation, you have not just directly, actually you have a formula for cube, but if you don't know the formula for cubic equation, you can also find this cubic solution by looking at the last term, okay? Because all the roots here, this last term is the multiplication of all the roots. So then you start to compute like it is 8, you can just start for 8. It means that if you, one of this root can be 8, or can be a number that can be divisible by 8. Like 8 can be 4, can be 2, can be 1. And they can be also its pair, minus 4, minus 2, minus 1. So it means that one, okay, if this exercise or if this equation has one solution, okay, one real solution, has real solution, so it must be one of these points here, okay? Yeah, just like this. So if you check it well, just if you compare, when you have A plus b cubed, it's equal to a cubed plus 3a square b plus 3ab square and plus b cubed. If you compare this equation to this one, directly you will see that this is a and this is your 3 and c. Here it will be 3 times 2d squared plus, while this d is decreasing, this 2 is increasing. That's why you have here 12. Then 12 it is 3 from the formula. Then it will be 3a. A is what? A is the same as d because d is decreasing. 3, 2, 1. Instead, in the other part, like we have 2 is increasing. Okay? 0, 1, 2. So time 4. Then plus 2 is increasing also. 4, then 8. Okay? Just the point. So by looking at this, we know directly that this one is equal to this. So here we can just write d plus 2 cubed is equal to 0. Here we have 3 real roots, and these 3 real roots are equal, are the same. Okay? They are the same. What does it mean? It means that here d will be equal to minus 2, minus 2, and minus 2. Okay? Just be careful with this one. I have to write all these roots. Even though they are equal, I cannot just come here and say d is equal to minus 2. No. We have 3 roots here, and these 3 roots are equal. So how to write when these 3 roots are equal? So CF will be equal to Euler raised to mx. Then it will be what? It will be C1 plus x C2 plus x2 then C3. And I will stop here because I have only 3 roots that are equal. Now I will substitute Euler raised to minus 2, okay, C1 plus x C2 plus x squared C3. This is the solution, okay, for this equation. Nice. Let us see for another exercise. Let me check for another one. Okay, just let me jump. Let me see. Suppose we have y, okay, 3 dash plus y dash is equal to 0, and they are asking for y0 is equal to, let me see, y0 is equal to 0, and y dash of 0 is equal to 0, 2, and y double dash of 0 is equal to 0. Okay, how to find this one? See, this equation, you just come here and you find this is 3, this is y, 1, sorry, then you are going to have y. Okay, just find first the auxiliary equation, write the auxiliary equation, what will it be? D raised to cube and d plus d, okay, and it's equal to 0. This equation here, as we can see, it's very easy to solve, so it will be d, just take common d, this will be d squared plus 1 equal to 0. Okay, now see, here we have d is equal to 0, okay, then we have d squared and d squared plus 1 must be equal to 0. So it means that this one, this part over here, will be equal to d squared minus 1. Okay, we know that in domain of real, there is no number that its root is negative, but we are solving not for real only, we are solving also for imaginary numbers. So we can just solve for this one. So this will be, d will be equal to, for this one, I know that this will be I square. Okay, so now it will be plus or minus, okay, plus or minus I square in this root. Okay, now it means that d2 and 3, d2 and d3 will be equal to plus or minus I. Okay, What does it mean? It means that we have here three roots. 0. Okay, these three roots are all different, but we have a pair of imaginary number. We have a pair of imaginary number. Okay, that is plus I and minus I. This is pair of imaginary number. Now see, here I have to combine. The solution will be one real number that is different from each other. So for real numbers that are different, we know that the solution will be Euler raised to mx times C1. But for imaginary number, okay, for a pair of imaginary number, we know that the solution will be Euler raised to alpha times x, and here C1 cos beta x plus I, okay, plus I sinus beta x times C2, okay, time C2. And that's the point. See here, that's the point. Okay, it means that here we will have combined. So CF will be only one solution that is real and different from each other. So Euler raised to 0, okay, 0x times C1 plus Euler. What is alpha here? Alpha is the real part. This solution has not real part. Here the real part is 0. That's why alpha here is also 0 times x. Then C1 times cos. What is beta? Beta is the imaginary part, the number that is multiplying this I, imaginary number. Here it will be 1 only. So it is x plus I sinus x also times C2. Okay, so in a nutshell, you can just write this will be 1, this will be 1, this will be C1 plus sorry, it's not 1, it is C2, and here C3, because here we have 3. Okay, the order of this equation is 3, so C1, C2, just be aware. So this will be C2 cos of x plus I C3 sine of x. This will be the solution. Okay, this will be the solution for this exercise. Okay, now see, this is the solution. Now how to find, okay, they are looking for, like, we want to find what is C1, what is C2, and what is C3. Just by finding this one, to find this one, this and this, you have just to substitute. Put y when x is 0. Okay, where you see 0, where you see x here, put x 0. This is very easy. How to find y? This is to find y. Okay, y has to be 0. Okay, for x equal to 0. Just solve this one. See in this equation, put y equal to 0 when x is 0. What is y? Y is the result of this solution. This CF is your y. Okay, this CF is your y. Now, so when y is 0, you put here 0 is equal to C1 plus x is also 0. This is for y 0 x 0. Okay, y 0 x 0. Then just substitute in this. 0 C1 plus C2. Cos of 0 is 1, so we'll put just multiplying by 1, it's the same. Sinus of 0 is 0, so this is the first equation. Okay, now the second, for y dash equal to 0. Okay, for y dash equal to 0, and they say also x is 0. What will it be? So I will pick up this expression and I will derive this equation. I have to derive this equation to find y dash equal to 0. So what will it be? Y dash derived. Okay, just put here 0 and derive this expression. This will be 0, and this one will be, okay, this one will be, this is equation 1. This will be 0, this one will be minus sinus. So C2 negative sine of x and here it will be plus I C3 sine, sorry, cosine of x. Then substitute for x equal to 0. Put x 0, here it will be 0. Put x 0 will be 1. So it means that the second equation, 0 is equal to I C3, okay? I C3 is equal to 0. This is the second equation. Let me write here, this is, okay, the first equation. Are you getting what I did? Okay, nice. After deriving this, then apply for x equal to 0. Deriving this will be 0, this will be minus sinus, this will be cosinus, I cosinus. So when I put 0, this will be 0. 0 for x, this will be 1. It means that here, from here, I can say that C3 is equal to 0 directly. Okay? So C3 is equal to 0. This is my second point. Now they said again, okay, for y double dash equal to 0, x 0, find. Okay, let us find what will happen here. See, here just pick up this term and derive again. Okay, so it is minus sinus, 0 will be, if I derive 0, it's 0. So this expression derived will be what? Minus C2. Sinus will be again cosinus of x, plus, if I derive this one will be minus I C3, then sinus of x. And I put for x equal to 0. X equal to 0. This will be 0. This will be 1. Okay, this will be this one. So it means that I will have 0 is equal to minus C2. It implies that C2 is equal also to 0. So if C2 is equal to 0, what does it mean? This is my third equation here. Okay, now see how to find then what is C1. We said that C2 is 0, C3 is also 0. How to find C1? That very easy, very simple. So it means that C1 is also 0. Put here C2 0, C1 is 0. Okay, so it implies that C1 is also 0. Now that you find C1, C2, C3, and so on, you will find that this particular, because when we do this, it is to find particular solution. Okay, yeah, particular solution of this differentiation equation or differential equation. So this particular solution, where the C for, like you can just come here for y 0 0, y 0, y dash 0 equal to 0, and y double dash 0 equal to 0. Okay, so it means that I will have CF, or my particular solution, okay, particular solution for this exercise will be all 0. All will be 0. Just put 0, 0, 0, 0. Okay, y will be 0. All will be 0 directly. There will be no space for anyone. All will be 0. Nice. Okay, so in the next video we will just bring a bunch, too many exercises about this one, too many different types of exercise that you can see in this topic. Okay, so they will just start you just to have an idea, and then we can just yeah, take those big waves. Nice. Okay, thank you. See you when I see you.